Hi, today we're going to look at the viscosity of some simple household materials that you likely have in your house. So what we have right here is our setup. I have stacked a group of books and put a ruler underneath one to create a platform. And what we're going to do is we are going to add our different liquids to a baggie. We're going to poke a hole in the baggie and allow the liquid to drip into a plastic cup underneath. We're going to allow it to drip for 20 seconds. When it is done dripping, we are going to get the mass of the cup and the substance that's in the cup to see which substance had the greatest flow. We know that viscosity is a measure of the flow of a substance. And so we're trying to test to see what substance has the best flow. So here you can see the procedure for poking a hole through your baggie for the liquid to flow through. I'm going to take a thumbtack and poke it through one corner of the baggie. I'm going to be careful to only poke one side and poke it straight through and then back through so that I have a very controlled hole for my substance to flow through. Then I'm going to take a piece of tape and tape it over the hole I just created so that I control the flow as it enters the cup. So to begin, I'm going to test the viscosity of water. Right here, I have a beaker of water. You don't have to use a beaker. I'm just using it to measure out 1/2 cup of water. So I'm going to add my water to the cup. And I'm going to pour this 1/2 cup into my baggie. Once I have it all in there, I'm going to seal my baggie. And then notice that I have my baggie tilted toward the side where I had my hole. So what I'm going to do is take my sealed baggie and I'm going to wrap the baggie over the ruler so that it hangs, and I'm going to use a binder clip to hold the baggie in place. Underneath, I'm going to place a clean and dry cup and get ready to start my experiment. I have a timer that's set to 20 seconds so that I'm consistent with my timing. At this point, it would be much easier if you had an assistant to do the timing and call time while another person is monitoring their setup. I don't have an assistant today, so I'm going to do it myself. So I'm going to get my timer ready. I'm going to, at the same time I take the tape off, push start on my timer. And I'm going to allow the water to flow into the cup for 20 seconds. When the time is up, I'm going to take the water away from the hole that I've punched more toward the top and move my baggie off to the side. Then I've got a simple balance here that I bought on Amazon, and I'm going to check the mass of my cup and my water. So the mass that I'm registering for the cup and the water is 13.04 grams. 2 additional water trials gave a total of 12.98 grams and 13.21 grams. Now, using the same procedures as with the water, I'm going to measure the viscosity of dish soap. I have my baggie with the hole already punched in it. I'm going to measure out 1/2 cup of dish soap and then add it to my baggie just like I did with the water. Once again, I'm going to seal the bag. And I'm going to fold my baggie over the ruler so that I have approximately the same distance between the baggie and the cup as I did on the last experiment. Once again, I'm going to pull my tape while starting my timer and allow the dish soap to drip into the cup. As you can see, this dish soap is not dripping near as quickly as the water. That is a sign that we have changed viscosity as we moved from water to dish soap. Okay, the time is up. I'm going to take this around. And now we can measure the mass of the dish soap that was added to the cup using the same balance. This time my mass is 9.34 grams. 2 additional trials with the dish soap were completed. Trial 2 had a mass of 9.12 grams, while Trial 3 had a mass of 9.22 grams. The final substance I'm going to test is light corn syrup. Using the same setup that I had earlier with the hole and the baggie, I'm going to measure out 1/2 cup of the corn syrup. And add it to the bag. Making sure we get our entire 1/2 cup of corn syrup into the baggie so we have the same measurement each time. I'm going to seal my baggie. And once again, fold this around using my binder clip to hold it in place. And my clean and dry cup underneath. So I'm going to start my timer for 20 seconds when I remove my piece of tape. Okay, I'm going to take my corn syrup off and measure the cup. And the mass I get is 8.83 grams. 2 additional trials with the corn syrup were performed, with Trial 2 having 8.74 grams and Trial 3 having 8.48 grams. Looking at the results of our experiment, water flowed out more quickly than either of the other 2 substances. Dish soap came out next, and corn syrup barely dripped out. From this, we can rank them. Water has the lowest viscosity, corn syrup has the highest, and dish soap is somewhere in between the 2. So the real question is why these liquids flow at different rates. The answer lies in intermolecular forces, the attractions that molecules exert on each other. One important type of intermolecular force is called the van der Waals forces, which includes London dispersion forces, dipole-dipole interactions, and hydrogen bonding. This is from Lopez and Lopez, Duran in 2018. These forces may be weak individually, but when you have billions of molecules in close contact, as in a liquid, they add up to make a noticeable difference in how a liquid behaves. The stronger the intermolecular forces, the more tightly molecules stick together, and the harder it is for them to slide past one another. This resistance to movement is what we observe as viscosity. That is from Robinson et al., 2021. Let's apply this to the 3 liquids in the experiment. Water has hydrogen bonding, which is a strong type of van der Waals interaction. However, water molecules are very small and light. So even though they form hydrogen bonds, they can break and reform those bonds quickly, letting the liquid flow easily. This is why water has relatively low viscosity. Corn syrup is different. It contains large sugar molecules like glucose and fructose dissolved in water. These molecules are bulky, and they have many sites where hydrogen bonding and London dispersion forces can occur. Because of these strong and numerous intermolecular attractions, corn syrup molecules cling tightly to one another. This makes it much harder for the liquid to flow. That's why syrup is so thick. It's essentially molecular stickiness due to van der Waals forces. This is from Krieger, 2020. Dish soap has a unique structure. Soap molecules are long chains with a polar head and a nonpolar tail. The polar ends interact with water through dipole-dipole forces and hydrogen bonding, while the nonpolar tails interact through London dispersion forces. These combined interactions create a liquid that is thicker than water, but not as sticky as syrup. In conclusion, this experiment shows how molecular interactions translate directly into physical properties we can observe. Water's weaker intermolecular forces mean low viscosity and a fast flow. Dish soap's more complex molecular structure means moderate viscosity. Finally, corn syrup's strong van der Waals interactions mean high viscosity and slow flow. Viscosity is more than just a science term. It's critical in real life. Motor oils are designed to maintain the right viscosity at different temperatures so engines don't wear down. Food scientists rely on viscosity when designing syrups, sauces, and drinks. Chemical engineers control viscosity in soaps and detergents to make them easy to pour, but still be effective in cleaning. That is from Kussler 2021 and Robinson et al. 2021. So when we see water pouring freely, dish soap sliding slowly, and syrup barely dripping, we're really seeing van der Waals forces in action.